Hi, and welcome to the videos for section 10.7. There's 4 videos for this section. Little bittersweet, this is the last section we're doing for this semester. This section, save the best for last here. Maybe not, but we'll pretend. Section 10.7 is partial fractions. And the long name, if you want to look at it, is partial fraction decomposition. What this chapter, or what this section of the book is about, is the following. Let's say, so up until this point, we had 1 over x minus 1 plus 1 over 2x plus 1. So by finding the LCD, multiplying numerator and denominator, get common denominators, combine all the terms. So by finding the LCD, etc., this would be combined into 3x over 2x squared minus x minus 1. With everything we've been doing all semester, we've been doing what? We find one method and then the reverse. So we have a function, then we find the inverse function. Or we have a matrix, and then we find the inverse matrix. That's essentially what this section is doing, is saying if I start with this guy, how can I get back to where I split this apart into a bunch of individual fractions? And there's 4 cases, thus the 4 videos. The first case is that the denominator let me redo that. So the denominator is a product of distinct or unique linear factors. The key here, distinct linear. Linear means what? X to the first degree. Distinct means what? None of them are the same. So I might have, in this case, x minus 1, 2x plus 1. That's what this guy is. If I factored it, it's x minus 1, 2x plus 1. Factor this. These are both linear, x to the first power, and they're different, or they're distinct. That's case 1, and so we say the following. This is how we go about solving these. Suppose q of x, so the denominator, can be factored as q of x is equal to, so a1x plus b1, a2x plus b2, etc., 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 all the way to anx plus bn. So some coefficient of times x plus b1, which is different than anything else. Again, it's essentially saying none of these factors are repeated. So it can be factored as that with no repeating factors. If that's the case, then I can say that my polynomial, or my rational expression here, p of x over q of x, where I have a polynomial in the numerator, polynomial in the denominator, can be broken up as a1 over a1x plus b1 plus a2, a2x plus b2, etc., 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 however many I have. And once I have that, then I can go ahead and solve a fraction equation, basically. So let's look at an example. So let's say we want to find the partial fractional decomposition, PFD, of 5x plus 7 over x to the third plus 2x squared minus x minus 2. So, if I do factor by grouping, and this is not a video on factoring, so I'm not going to take all that time, but I could factor out an x squared here, factor out a minus 1, factor it again. This thing factors into x minus 1, x plus 1, x plus 2. And again, that's by factoring by grouping, which I'm not going to do here, in the interest of time. So I'm going to erase this so I have plenty of room to write here. So, off of what I erased there, I can rewrite this thing, my original, as sum a1 over one of the factors, x minus 1, plus sum a2 over the second factor, x plus 1, plus a3 over the last factor, x plus 2. So now, let me tell you a little bit. So there are, what we have, there's some method called a zero substitution method, which is to say, not zero substitution, but a zero method. So what I would want to do is I'd plug in, not yet. First I have to do the LCD. So let me do that first, then I'll talk about that method. So if I have, for example, an equation, what, x over 3 equals 2 over x minus, I don't know, whatever, x over 4. I can simplify this, what, by finding the LCD, multiply everything by the LCD, and it gets rid of the fractions. I'm going to do that same step here now. Well, my LCD is what? It's this guy. It's what I'd already figured out. So I'm multiplying this by every single piece in this equation. So when I do that, what happens? On this side, if I multiply x minus 1 times x plus 1 times x plus 2, well, all of these cancel with all of these in the denominator, and I'm left with what? Just what I have up here, 5x plus 7. Here, if I multiply by the LCD, so x plus 1, x minus 1, x plus 2, well, the x minus 1's cancel out, so I'm left with what? I'm left with a1 times x plus 1, x plus 2. Same thing here, x plus 1, x minus 1, x plus 2. The x plus 1's cancel out, so I get a2 times x minus 1, x plus 2. And then lastly, same thing here, x plus 1, x minus 1, x plus 2. The x plus 2's cancel out, so I get a3 times x minus 1, x plus 2. So, now this is where I was talking about this other method. I'm not going to go through it. Again, it's called like a zero out method because it doesn't work all the time. And hopefully by now you guys have watched enough of my videos that you know I don't like showing you things that don't work all the time. Because otherwise, what happens on the exam if the question that's on there happens to be one of the cases where it doesn't work all the time? Now you end up doing it wrong, or you get to a position where you don't know what else to do to solve it. So I just don't like doing that. Sometimes, like the zero out method would be quicker on this one, I'm not going to lie, but it's better to just do it the longer way, do it the long way every single time, and then you know at least you get the right answer every time. So let's expand this out. So this thing, if I FOIL this, I get what? X squared plus 3x plus 2. Whoops, not there, just to there. I get what? X squared, so plus 2x minus 1 is plus x minus 2. And this one, if I FOIL it, I get x squared minus, what did I do here? Why are those two the same? This one, I canceled out the x plus 2's, so this should be x minus 1, x plus 1. So again, I knew stuff can't, that's why I had to stop. I knew stuff canceled out, so these two shouldn't have been the same. It's because my x plus 2's canceled out. So I get x minus 1, x plus 1. So I get what? That's a difference of squares, so I get x squared minus 1. So now let me distribute the a1's, the a2's, the a3. So I get what? I get 5x plus 7. Okay, that's fine. So let's look at So I have here what? I have a1 times x squared, a1 times 3x, a1 times 2. And then a2 times x squared, a2 times x, a2 times negative 2, and so forth. So out of each of these pieces, I have an x squared. This one is what? a1 times x. So, you know what? I'll do one more step, and then we'll show you how it breaks down. So this is what? This is a1 times x squared plus 3 times a1 times x plus 2 times a1. Then you have plus a2 times x squared plus a2 times x minus 2 times a2. And then last but not least, what? a3 times x squared minus a3 times 1. So now I want to group all of my like terms. So I have what? I have an x squared here, I have an x squared here, and I have an x squared here. So with those three pieces, if I factor out an x squared, I get what? I get a1 plus a2 plus a3. So again, it's a1x squared plus a2x squared plus a3x squared. Factor an x squared out of those pieces, and I'm left with a1, a2, a3. How about the x pieces? Well, if I factor out an x, so let me circle these so we can keep track of what we're doing. There's an x piece. There's an x piece, none down at the end. So when I factor out an x, I get what? 3 times a1 and plus a2. And then last but not least, the constant values, so the pieces that don't have an x attached to them, I have what? 2a1 minus 2a2 minus a3. And this is all equal to 5x plus 7. So now, this is where we're going to start comparing sides of the equation. If you think back to when we were doing logs, if I had like log of x equals log of 12, that meant what? X has to be 12. That's the only way those two sides can be equal. Similar idea here. So on the left, I'm going to add in a 0x squared, just as a placeholder, so to speak. So if both of these sides of the equation are going to be equal, it means what? X squared piece, this coefficient has to be 0 so that it matches up with the coefficient over on the left. So that means a1 plus a2 plus a3 is equal to 0. That's the only way these two sides are equal, is if this value equals 0. Similarly, with the x piece, the value attached to the x, this one, has to be equal to what? Well, it has to be equal to 5. So 3a1 plus a2 has to be equal to 5. The only way these two sides of the equation can be equal, with 5x on the left, is if this is equal to 5x. And then last but not least, the constant value, so the 2a1 minus 2a2 minus a3 has to be equal to this guy over here, which is 7. So now I have what? Now I have a system of equations, and you can solve this however you want. Substitution, elimination, Gaussian elimination, reduced row echelon, Kramer's rule. You have so many different ways you can go about this. If we do that, and again, in the interest of time, I'm not going to go through the solving of all this, but when you do, you end up with A1 is equal to 2, A2 is equal to negative 1, and A3, let's see, A3 is equal to negative 1. So therefore, going back to this original, so I'm going to erase this here, so hopefully you can hit pause if you need to follow back through, but I need a little bit of room here. So we have what? We have this original 5x plus 7. Let me write it in green, our final answer here, so we can keep track. So we have 5x plus 7 over x to the third plus 2x squared minus x minus 2 is equal to a1, which was 2, over x minus 1, plus a2, which is negative 1, over x plus 1, plus a3, which is negative 1, over x plus 2. So that's the expansion, that's the decomposition of this rational expression, breaking it out into its different factored pieces. So again, a lot of algebra here. Got to be careful with the signs, especially when you're dealing with the negatives, but that's the process when we have distinct linear factors. So come on back and we'll look at option number 2, or possibility number 2.